Now, okay, so a picture of the number line. We could go a couple different strategies. I sometimes use like circle dots like this. But I think your textbook probably does like this. So just kind of like the set. So that means those square brackets means we're including the points at the end point, right? The left and the right end points. So this is A and B. What else can we do? I'll try to go a little bit faster here, but we've also got AB, which would be, and this time I'm just going to be lazy. I'm going to say X such that A less than X less than B. So if you're like, I don't need to keep writing X as an element of the reals, it's understood that we're working with real numbers. All right? In that context, it's okay to omit the element of the reals. Now, in some more advanced math classes you might take, it might not be okay. It might be important to stay where X is coming from. But in here, this is probably okay. The only exception to that, I would say, is we do sometimes talk about complex numbers. And for complex numbers, we don't want to use interval notation in here anyway. It has a different meaning in complex variables. Okay, so this is the so-called open interval. So this is closed interval. This is an open interval. Right? The number line. Like that, right? You got other choices, right? You can have the so-called Clopin interval. Or you could have the opposed interval. So you guys tell me, what would the set builder notation be for this one? I'll start you out. X such that what? What's my condition on X to be in that set? B is, let's see here, you're going to say B is greater than X is greater than or equal to A. Oh, that hurts my head. But yes, you could do that. I mean, that's actually fine. That would be logically equivalent to writing the following. Right? Like the same song and dance, same thing. This one, X such that A less than X less than or equal to B. So, you know, the closed includes the endpoint, the open excludes the endpoint. What other flavor choices do you have? You could have something like A to infinity, or you could have A included. So the first one, A is not included. The second one, A is included. So these are called open. The first one is called, well, they're both called rays. A ray is a set which starts someplace but goes on forever, right? And on the number line, they geometrically correspond to rays, right? Like the kind of geometric ray you might have saw in high school. So we have like that. Oops, I got to make that. See, I don't know. I mean, this notation's okay, but I really kind of prefer sometimes, and you'll see both in my solutions probably, you should understand that you have choices here. You could instead denote that ray like this. That'd be fine. That's like another choice we have for the number line for an open ray. And then for like the closed ray, it would look like what? You just, yeah, fill in the dot, exactly. And for me, I probably have an easier time when I'm grading to tell this versus that. See, you guys, sometimes the distinction between your square bracket and your curly bracket, it could get kind of dicey. You know? I mean, anyway, I shut up. Okay, so what are the other, can you think of other choices? What else can we do? You'll forgive me if I don't write the pictures for these, but we've also got minus infinity to a, not included, and minus infinity to a, included. So everything I'm writing on the board right now, these are examples of intervals. So when I ask for something in interval notation, we're asking for this kind of notation. Yeah?
When you have an infinity, it can have to be like a bracket, right?
Right, yeah. We don't include, infinity's not a number for us, so. There are people who work with like the real numbers with infinity tacked on. I mean, there's a meaning that can be given to that, but we will not include infinity in here. So if you count, how many we got? We got the whole real line, closed intervals, open intervals, and these half open, half closed intervals, right? So there's 1, 2, 3, 4, 5, 6, 7, 8, 9 different types of intervals, right? There's one other kind of interesting set, which is called a singleton. So a singleton is a set containing just one point. And what I have put on this board here are the 10 examples of connected subsets of real numbers. What's a connected subset of real numbers? So a set is connected in here, like an informal, a good definition for this is a set is connected if I can draw the set on the number line without lifting my marker. So if you look at all of these, like I can draw the whole, I mean, you got to use your imagination a little bit. We're imagining we can draw infinitely long, right? But if you can imagine me starting to draw at minus infinity and just keep drawing and drawing and drawing and drawing and drawing and drawing and drawing, I have the whole real line, right? That's a connected subset. This I can draw from here to here without lifting my marker, right? Here to here without lifting the marker. Without lifting the marker, without lifting the marker. You see all these, you don't ever have to lift the marker. They're what are called the connected set. This one's kind of stupid. What's this look like? Yeah, it's just a dot, right? Yeah, pretty much I definitely want to use, yeah, I guess I got to do a dot. That's right, yeah. I was thinking, should it be an open? No, it's got to be that one. All right. So next up, you're like, well, this is very limiting, right? If I'm using interval notation, I can only talk about these 10 kinds of sets, but there's other things that happen, right? So, for example, what if we wanted to look at the solution to absolute value of x greater than 1? So what is the solution set to the absolute value of x greater than 1? How would you think about that? See, the way I'd think about it is I'd think, okay, well, absolute value of x I can graph, you know? It's a v, like that. And if I'm asking to be greater than 1, that means I'm looking for points on the graph that are like above 1. So my solution set I can visualize as being these points over here and these points over here. Now, what I'm doing right now is probably something we're going to cover later in the course. So if you're not comfortable with what I'm doing, it's okay. It's okay. I'm really just trying to get you to the point of seeing that the solution set here, it has two different pieces, like the piece over here and the piece over there, right? So over here, on the right, we're looking for x greater than 1, right? But over there, what are those kind of, this is for that x, right? Really, the x is here, I suppose, but yeah, over here, x is what? X is what you say? X is less than what? Yeah, 1 is, negative 1 is what we want, because that's minus 1. So x less than minus 1 or x greater than 1. X less than minus 1, that would mean This would say x is an element of what? X is an element of, oh man, this marker's sad. Minus infinity to minus 1, not included. Whereas this over here would say x is an element of 1 to infinity. Right? So if I wanted to express the solution set for this, I couldn't do it with a single interval. I need set operations, right? So here, and we'll end class with this, but the solution set would actually be minus infinity to minus 1 union with 1 to infinity. Have you guys talked about unions ever in your previous math classes? Yeah? So we could use unions to get to more exciting kinds of sets, which are called like this is a disconnected set, right? If I graph this on the number line, what's it look like? Right, yeah, infinity to minus 1, and then it picks up again here at 1, right? So as you can see, I can't draw that without doing what? I have to lift my marker off in order to draw that on the number line. It's a disconnected set, it's not connected. So anyway, I hope you now are, if I ask you for an answer in interval notation, you know what I mean now, right? And sometimes we have to use union to get to more interesting things. I'll shut up. See you guys Thursday. Thanks. Oh, can you hit the record button? Thanks. It's on the side. You got it?